What defines our reality? How do we make sense of what exists and what does not? We exist, that much is certain. Even if our experience of reality is just some dream or the simulated experience of a brain in a vat, the experience itself is undeniable. We can doubt whether the reality that we are experiencing is a truthful representation of the world, or somehow just an illusionary manipulation designed to deceive us. But the very act of doubting itself is evidence that we exist, at least in some shape or form. But what else exists? What, other than our subjective experience of the world, can we actually presume to be real? In the previous episode, we explored the question of, if a tree falls and no one is around to hear it, does it make a sound? The aim of that video was to ask whether things could exist without our perception of them. All throughout the video, we defended the view that so long as a thing, such as a sound, could be perceived, then we would presume that it did in fact exist. Towards the end of that episode, we tried to envision a world in which sound could never be perceived. For this, we tried to imagine a world, a parallel universe, in which life had never developed the ability to hear sound. This was a world in which no living being ever had, nor ever would, experience the qualia of sound. We came to view sound as something that did not exist in and of itself, but rather that existed as a relationship between subjective experience and the physical reality that brought it about. Finally, we asked ourselves the question, if this universe were entirely shut off from our own, if there was absolutely no way for their world to communicate with ours, for us to experience their sounds, could we still say that theirs is a universe in which sound exists? And to this we concluded that no, a sound that cannot be perceived does not exist. The existence of a sound depends on there being someone or something with the ability to hear it. Today, we're going to be abstracting this idea out a little further. Rather than asking whether the tree that falls with no one around to hear it makes a sound or not, today we'll be asking, if no one is around to observe it, does the tree even exist? Hi, my name is Thibaut and I make videos on philosophy and science. Today's episode is a follow-up to our previous essay, But What is Sound? So if you haven't checked that one out yet, I would highly recommend that you start there first. Also, I feel like I should be issuing a bit of a warning with this one. Today's essay is going to get pretty metaphysical. Today, we're talking about ontology. More specifically, we're going to be asking ourselves the following question. What exists and what does not? Now, this is a pretty heavy question, obviously, and it's going to take us through a lot of complicated stuff. Today we'll be touching on such topics as quantum physics, event horizons, and parallel universes. Yeah, this one's going to get deep. So if there are things in this video that you find hard to understand or that just straight up don't make any sense, don't beat yourself up about it. The responsibility of communication in this relationship lies more so with me than it does with you. And as hard as I try to make my content as digestible as possible, this simply is a highly conceptual subject. And it's just very likely that my explanations end up being unclear. It's also quite possible I'm talking out of my arse on this one, but I guess we'll see. Either way, if you do manage to make it to the end of this video, give yourself a round of applause, because this one ain't easy. Lastly, if at any point it feels like we're getting a little sidetracked, just remember that ultimately we should be circling back to that same underlying question. What exists and what does not? If you recall from our previous video, we mentioned how in the visual microphone experiment, a team of researchers at MIT were able to recover audio from a video recording. Essentially, what they did is they set up a camera on the outside of a room looking in through a bay window at a bag of crisps. They then played a recording of the nursery rhyme, Mary Had a Little Lamb, next to the bag of crisps. And based on how the crisp packet was vibrating in the recorded footage, the experimenters were then able to recover some of the original audio that was being played inside that room. Now, the reason that we brought this up was actually to play devil's advocate a little. What we were saying was that, even if nobody was inside the room to hear the recording, so long as information could leave the room, even if it was in the form of electromagnetic radiation, then we would presume that the sound could be perceived, and thus existed. Next, we imagined a faraway alien civilization that was looking back at Earth with a high-speed and high-resolution camera. Because these aliens lived 1.4 billion light years away, the light that they were receiving from Earth was light that was emitted 1.4 billion years ago, so around the time of the Proterozoic, a period where no living organism on Earth was yet able to hear sound. To reiterate our point here, basically what we were saying was that those aliens, over 1 billion light years away, were able to hear sounds that would have otherwise been left unheard from Earth 1.4 billion years ago. And again, we don't actually care about whether this is practically feasible or not. We're just being as lenient as we possibly can in our interpretation of what is perceivable. In fact, let's just ditch the whole sound idea altogether and make this as explicit as we possibly can. If information can travel between 2 points A and B, then we shall presume that any event occurring on point A can be observed, detected, or registered from point B, and vice versa. Thus we assume that any event, such as a sound, exists so long as it exists in relation to some observer. So what about an event that occurs independently of an observer? This is something that we had just started touching on towards the end of the previous episode. In the end, we concluded that, in order to understand what it would mean for an event to occur truly independently of an observer such as ourselves, we would first have to imagine a parallel universe in which this event occurred, entirely distinct and separate from our own. In Euclidean geometry, two lines are parallel if and only if they never meet, no matter how much we might stretch them out on either end. When we say that two universes are parallel, therefore, what we mean is that these universes never meet, no matter how far out we decide to stretch them in either time or space. Now, just so we're clear on this, I'd like to make a distinction here between what we've just come to define as a parallel universe, and contrastingly what we'll refer to from now on as tangential universes. Again, in geometry, tangential lines are lines that intersect at least a given point. Instead of running parallel to one another and never touching, tangential lines do meet. Essentially, what we mean by tangential universes, therefore, are universes that branch out from one another at a given point in time or space. For example, we might entertain the idea of a universe in which JFK was never shot. We could say that on the 22nd of November 1963, two separate timelines branched out from one another, one in which the bullet missed him, and the other being the timeline in which we find ourselves today. Even if these two universes have now become causally isolated from one another, i.e., the events from one universe can no longer affect the events of the other, they still share a common point of origin, a common history. Thus, according to our definition, these two universes, these separate timelines, are not considered parallel to one another. They are tangential. Another example to help illustrate this idea would be to think of the experiment of Schrödinger's cat. In this, a cat is placed inside a box, with its fate depending on whether a given particle in the box will decay or not. This particle has exactly a 1 in 2 chance of decaying, and until we open the box, we cannot know which of those two events has taken place. According to quantum mechanics, until we make that observation, we must accept that the particle exists in a superposition of states, both decayed and not decayed at the same time. And thus the cat must also exist in a superposition of states, both dead and alive, until we open up the box and the observation is made. One interpretation of this idea of superposition is what is commonly referred to as the many worlds interpretation of quantum mechanics. Essentially, what the many worlds tells us is that reality is one giant multiverse, with a near infinite array of individual universes branching out from one another at every possible moment in time. In this multiverse hypothesis, each and every event occurs simultaneously, with the act of observation merely telling us in which universe we happen to find ourselves. So, the point that I'm trying to make here is that these universes, the ones that are often portrayed in popular media, aren't really parallel as far as we're concerned. They are tangential. This is a noteworthy distinction to make, and we'll find out why that is exactly in just a minute. But, for the time being, just remember that whenever we talk about parallel universes, we mean it in the strictest possible sense, of two universes that never meet at any point in time or space. Otherwise, we shall use the term tangential, okay? I want to give you a little bit more of a feeling of what I mean by tangential, and for that we're going to have to talk briefly about cosmology. Back in the 1920s, a man by the name of Edwin Hubble was looking through his telescope at the Mount Wilson Observatory when he noticed something a little peculiar. The sky that he was observing seemed to contain far more red stars than there were blue ones. Intrigued, Hubble quickly deduced that this apparent discrepancy in hue had to be in some way a manifestation of the Doppler effect. Have you ever noticed how when a car drives by you, the sound is higher pitched as the car approaches, but then lowers in pitch as the car is moving away? This is what is known as the Doppler effect. Essentially, what is happening is that the sound waves are being compressed as the car is heading towards you, and thus are higher pitched, whereas as the vehicle drives away, the sound waves are now getting stretched out into those lower pitches. Hubble theorized that the abundance of red stars in his observations must be due to the same underlying principle. Red and blue lights are both forms of electromagnetic radiation, with the blue lights corresponding to higher frequency wavelengths, while the red is associated with somewhat lower frequencies. When we observe a star and its light is redder than we expected, essentially what this means is that the light that the star had originally emitted has been dilated and stretched out before reaching us. This is what is known as redshift. If a night sky presents more red stars than there are blue ones, then this must mean that there are more stars moving away from us than there are stars travelling towards us. From here, it only takes a little stretch of the imagination to realise that, if most of the stars in the universe are moving away from one another, then this must mean that the space in between those stars is dilating, that the universe itself is expanding. Eventually, with continued observation of the night sky, Hubble calculated that the universe was in fact expanding at a rate of around 70 kilometers per second per megaparsec. To put this into terms that we might somewhat be more familiar with, if we were to take two galaxies roughly 3.3 million light years apart, then the expansion of space happening in between those two galaxies would make them appear to be travelling away from each other at a rate of around 70 kilometers per second. An analogy that's often used to illustrate this idea of an expanding universe is to compare it to a loaf of raisin bread. On a quick side note, does anyone in the 21st century even eat raisin bread? Is it just me, or does this analogy seem hella outdated? Imagine that the raisins in the bread are distant galaxies. As the dough rises, the space in between those galaxies expands. The rate at which those raisins are moving apart from one another is what we are referring to as Hubble's constant. Now, Hubble's constant is based on how far apart each raisin is from one another. So if we start off with two raisins that are quite close together, say 1.5 centimeters for example, then by the time the loaf is baked, those raisins might now be 6 centimeters apart. But if we started with two raisins somewhat further away from each other, say 9 centimeters for example, then by the time the loaf was baked, these two raisins would now be 36 centimeters apart. What this means in practice is that the further away a galaxy is, the faster away from us it will seem to be travelling. At a rate of around 70 kilometers per second per megaparsec, a galaxy that is 1.4 billion light years away will seem to be travelling away from us at around 10% the speed of light. A galaxy 10 times further away than this, 14 billion light years, will appear to be moving away at the speed of light. Now, before you start saying, that's impossible, nothing can travel at the speed of light, technically the galaxy isn't actually moving away from us at that speed. Instead, it is the expansion of space itself which is happening at that rate. This is an important, if not a little finicky distinction to make, and if you're curious as to why that is exactly, then I'd strongly recommend you go check out Event Horizon's video on the subject. So, a galaxy 14 billion light years away would appear to be travelling away from us at around the speed of light. This means that if an alien in that faraway galaxy were to shine a torch directly at us, the light from that torch would never actually reach Earth, since the stretching of space in between our two galaxies would be occurring at the same rate as the speed of light. Beyond a distance of 14 billion light years, therefore, all regions of space effectively become causally isolated from one another. Okay, so technically this isn't quite correct. The figure of 14 billion light years actually corresponds to an estimation based on the current rate of expansion, However, this constant has been evolving over time, which makes things a little more complicated. The true figure of where this alien would have to be is actually closer to 16 billion light years, so a little further than the 14 billion we just mentioned. This is what is known as the cosmic horizon, or event horizon, as opposed to the Hubble horizon that we were referring to thus far. This is a bit of a technicality, I'll admit, but honestly it just wouldn't have felt like a Curious Tea video if we didn't get just a little bit pedantic.
I agree as well. Shallow and pedantic.
Okay, so now we're getting into the territory of tangential universes. Remember earlier when we were talking about an alternate universe in which JFK was never assassinated, and how the two separate timelines had become causally isolated from one another? Well, just as the effects from one timeline could no longer affect the events of another, two regions of space that are further apart than their respective event horizons will also be unable to influence each other. Just like the idea of two alternate universes branching out from one another, two regions of space can also become causally isolated when the space in between those raisins is expanding at a greater rate than the speed of light. Because our universe is continually expanding, there will come a time when our extraterrestrial neighbours too will also reach this event horizon, and thus they will no longer be able to communicate with us back here on Earth. So what would that mean for an event occurring on planet A from the perspective of planet B? If the two regions of space have now become causally isolated from one another, could an event on planet A still be observed by planet B? From the perspective of planet B, could the event still be said to exist? Alright, so here's where the distinction between parallel and tangential universes comes in handy. Those two regions of space represented by the points A and B do not run parallel to each other, since they do still share a common point of origin, and yet now they have become causally isolated from one another. Any event occurring in one of these two regions will now no longer be able to affect the timeline of the other. This is what we mean by tangential universes, right? The region of space that is 16 billion light years away is not in some universe running parallel to ours, it is simply on a different tangent. In practice, what this distinction means is that the events occurring on planet A aren't happening completely independently from those on planet B, since they do still share a common history. Here's what I mean by that. Say that there is a tree that's just about to fall on planet A. Our alien neighbours have been patiently waiting for this moment, and are now watching attentively through their giant telescopes. Now, the trunk of the tree has just snapped. The weight of the object comes crashing down, but just before the tree hits the ground, planet B crosses the event horizon. Planet B is now no longer able to observe the unfolding of this event. This is just like watching a movie that cuts right after the cliffhanger, right? So, did the tree fall or not? Well, I mean, there's very little chance that it didn't. Unless somehow Superman magically swoops in just in the nick of time to save the day, then it's pretty much a done deal. Though the Superman scenario does seem a little unlikely. Unlikely, but not impossible. Now, before I get laughed out of existence for saying that Superman exists, just imagine something else, like a sudden gust of wind that picks a tree back up and puts it on its stand, or whatever. The moral of the story is, there is a probability for every event. Imagine instead of the tree falling, we rerun the experiment with Schrödinger's cat. In this variation, we place the cat inside a box with an unstable particle, close up the lid, and boom, planet B exits the event horizon. Now we open up the box on planet A. Although we now know which of those two events has occurred, the observers on planet B don't. All they have is a probability of what occurred, a 1 in 2. But that's still something. Because planet B is able to look into our past, even after we have crossed their event horizon, they still have some information about the state of planet A, and so they are able, at least in some capacity, to predict our future. They can at least make an informed guess about the state of planet A. Now, obviously they will very quickly run into problems regarding computational ability, chaos theory, and the Heisenberg uncertainty principle, but at least in theory, they should have some idea about what's going on back here on Earth. Again, just like in the previous episode, we're being as lenient as we possibly can. So, even after the planet has crossed the event horizon, the events occurring on planet A are still not happening completely independently from those on planet B. since the two still do share a common point of origin. In fact, every event in our universe shares a common origin. Every region of space has a history with every other. And what is that point of origin, you ask? Well, the Big Bang, of course. Every event in our universe exists in relation to every other because each and every one of them exists in relation to the Big Bang. All of these events share a common history, and so any event in the universe can theoretically be observed. And so the next logical question we could ask would be, well, what do we not share a history with? If everything in our universe exists in relation to every other, then what does not exist in relation to us? So I know that both from the title of this video, as well as my incessant insistence on distinguishing between parallel and tangential universes, that you've probably already figured out what the answer to that last question is. But let's just rewind for just a second here. After Planet B finally crosses the event horizon, the events on Planet A still continue to exist from the perspective of Planet B, right? They exist as probabilities, but they exist. And actually, I just want to touch on this notion of probabilities real quick. Earlier, when we were saying that, after opening the box on Planet A, the observers on Planet B only had a probability of which event took place. Actually, the observers on Planet A too only have a probability of which event took place. This might seem a little counterintuitive. It might seem like, after opening up the box, we have become absolutely certain of which event has taken place, of whether the cat is dead or alive. But perhaps it's not as certain as we might think. For example, maybe the cat actually did die inside the box, and without us looking, somebody quickly swapped the dead cat for a live clone. It might be impossible for us to tell the difference. In a similar manner, you might be 100% sure that you are, wherever you are, at home on your phone or in front of your computer, watching this video. But it could also be that you are just a brain in a vat, being stimulated in just the right way to make you believe that you are at home watching this video, when in actual fact you are in some evil laboratory, being prodded by a bunch of scientists for research purposes. Now, I don't mean to alarm anybody with any of these kooky conspiracies. The point here is simply that we never have certainties about anything, only doubts. All we can ever hope to have is information about things, but never quite knowledge. Information and knowledge are not the same thing, and ultimately this has to do with the inherently probabilistic nature of information itself, but we're just going to have to leave that on the sidelines for now. Even though there is a very strong likelihood that you are in fact at home watching this video, there is also a probability that the second option is true, and you can never know with absolute certainty which of the two is the case. The one thing that you can be certain of, however, is the very fact that you are doubting. The only thing in our universe that we can ever truly be sure to exist is the act of observation itself. Every event in our universe, therefore, must exist in relation to our observation of it. Every event is real insofar as it is an observed, registered, or predicted event. The reason why parallel universes do not exist is because there exists no relationship between them and any observation that we can make. This might seem like a very anthropocentric point of view, to posit that a universe can only exist when there is an observer such as ourselves to observe it. But the fact is, if we also allow for the opposite to be true, then we run into the risk of allowing anything to be true. For example, I could say that there exists a parallel universe composed entirely of pink elephants floating around in space, and there is no way of us to prove or disprove that this reality exists, since by definition parallel universes cannot be observed. Ultimately, we have to draw the line somewhere between what exists and what does not. If we allow for absolutely anything and everything to exist, then the concept of reality itself ceases to have any meaning. We become unable to distinguish between reality and non-reality. If we allow these kinds of universes to exist, then we run the risk of allowing any number of potential universes existing. Quite possibly an infinite number, in fact. And what becomes of our universe in relation to an infinite number of universes? The answer is undefined. Our universe would become meaningless, really. This would require a separate video to explain what I mean exactly by that, a video on why infinities do not exist, but I am nowhere near writing that script yet. All things that exist in relation to one another. Defining reality as the network between things that exist, and therefore non-reality as anything outside of those relations, is ultimately how we give our universe meaning. This is summarized quite meticulously in Chris Langan's CTMU.
Reality, i.e., the real universe, contains all and only that which is real. The reality concept is analytically self-contained. If there were something outside reality that were real enough to affect or influence reality, it would be inside reality. And this contradiction invalidates any supposition of an external reality.
Reality is all that there is. If there existed two separate universes, with neither of the two being able to influence the other, then it would seem meaningless for us to say, from the perspective of one of these universes, that the other one existed. I'm just going to say this one more time. All things that exist in relation to one another. Nothing exists in isolation. The timeline of our universe is constrained on the one side by the Big Bang. This defines the point at which time, as a concept, begins to have any meaning. On the other side lies the inevitable heat death of our universe. This heat death is a point in time far out into the future, where the entropy of the universe will be at its maximum, and where the fabric of space itself will be so stretched out that none of the regions of space will actually be able to communicate with one another. Every region of space, every particle, will effectively have become causally isolated from every other. This heat death is a moment in time without a future, a point where no new event will ever occur, since even the particles themselves will cease being able to interact with one another. Nothing exists outside of this reality. Every event, both past, present, and future, all that is real, all that exists within those boundaries. There can be nothing else, for if there were something else that could affect our reality, then it would already be a part of reality. Alright, I did warn you this one was going to get metaphysical. We've touched on a lot of deep subjects here, and there is a lot to digest. For now, I'll just leave you with a quick quote by John Wheeler, whose philosophy has been quite influential towards my own perspective on the matter. John Wheeler was a theoretical physicist, especially known for his conception of the participatory universe, a concept otherwise referred to as it from bit.
Stronger than the anthropic principle is what I might call the participatory principle. According to it, we could not even imagine a universe that did not somewhere and for some stretch of time contain observers, because the very building materials of the universe are these acts of observer participancy. This participatory principle takes for its foundation the absolutely central point of the quantum: no elementary phenomenon is a phenomenon until it is an observed or registered phenomenon.
I hope you enjoyed this video. I'm not gonna lie, this one was a bit of a leap of faith. I'm not 100% sure of any of the things that I've mentioned here. These are all suppositions, and it's your guys' turn to let me know what your thoughts are down here in the comments. That being said, if you like this sort of content, don't forget to like, share, and subscribe, as I will be making more videos like these in the future, and it'd be a pleasure to share them all with you. Alright, that's enough rambling for today. Stay curious, fam.